All right, so right now we're going to cover a special case of diagonalization where we're talking about symmetric matrices. And remember that symmetric means that A is A transpose. And really, here I should probably preface this with I'm only actually going to be talking about real symmetric matrices. So that's symmetric matrices with real entries. That's all the matrices we've really ever dealt with. So don't sweat this too much. So here's my kind of claim. So, couple of parts. I'm going to start with the big part first, and then we'll go back and pick up a couple little bits. So my claim is that if A is symmetric, right? So if A is A transpose and A is real, then we can write A as an orthogonal matrix times the lambda matrix times our orthogonal matrix's transpose. Now, this thing here is so special, this gets a fancy name, which is very cool. This is called the spectral theorem. So, in order to get there, I'm going to have to make a couple other claims. So, I'm going to go after those first. So, here are going to be my other two claims that come maybe before this thing. So, I'm going to take this guy, we'll scoot it down a little bit. We're going to make a couple claims before we start. So, claim one is going to be that if, oops, it's not going to be, well, it is going to be an if. So, it's if A is symmetric and A is real, then the eigenvalues of A are also real. So that's going to be kind of the crux of this argument. And then I'm going to have another claim. So I'm going to call that claim one. Then we're going to make another claim two here. And that claim is going to be the eigen vectors of a real symmetric matrix can be chosen orthonormal. And these are going to be the kind of, I'm going to make these two subclaims, and then once I've got these two subclaims, I'm actually going to automatically get the spectral theorem. That spectral theorem is really just a rephrasing of our diagonalization earlier. So remember that we said before, if we can find enough if we can find enough linearly independent eigenvectors, then I can always diagonalize using this form. This form is really just the lambdas, that diagonal matrix with the eigenvalues down the diagonal, and then the x and the x inverse are the matrices made out of the eigenvectors in the same order that the eigenvalues are in. So the trick here is that I'm going to be able to say, well, the lambda matrix, that's all real, and these vectors x are actually going to have the property that I can pick them to be orthonormal. And then this X matrix is going to turn into a Q matrix. And because everything's going to be square here, I'm going to know that Q and Q transpose are inverses. That's really kind of where I'm headed. But in order to get there first, we have a couple of claims to deal with. Okay, so first things first, let's grab claim one here, and we'll work on that guy. So if we're looking for I'm going to assume I have a symmetric real matrix, and then I'm going to show that the eigenvalues of that matrix are real. So first things first, I'm going to say, let's let let's let lambda and x be an eigenpair. And that's really obviously an eigenpair for the matrix A, right? So then I'm going to write down what that means. So that means that A done to x is lambda done to x. Oh, and I'm going to need to do one thing before I get too deep into this. I'm going to drop these vector hats because my goal is going to be to demonstrate that something's real. And in order to demonstrate that it's real, I'm going to need to talk about some complex conjugates, right? So I know I'm going to have this done when I find out that lambda is lambda conjugate. That's how I'm going to know that a complex number is real. Remember, we learned that in the complex numbers crash course. So that's my goal here. In order to kind of realize that goal, I'm going to need to take this equation, and I'm just going to transpose everything in this equation. So this equation is going to be equivalent to A transpose X, conjugate. A conjugate, X conjugate, is going to equal lambda conjugate X conjugate. And this is why I'm not using arrows. And this guy, I know that A is real, so I know that I can just swap, right? This to A X conjugate is lambda conjugate X conjugate, right? Okay, so then I'm going to take this equation here and I'm going to transpose both sides of it. So when I transpose both sides of it, I've got AX conjugate transposed is going to be lambda conjugate X conjugates transpose. And that's going to give me, whoops, we need to swap our order. So we're going to have X conjugate transpose A transpose is going to equal, lambda's here is just a scalar, so that's just going to chill. So I got lambda conjugate, just a scalar, that's chilling. And then I got X conjugate transpose. And then I know that A is symmetric, so I can rewrite this as X conjugate transpose A is equal to lambda conjugate X conjugates transpose. Okay, so I'm going to call this thing over here that I started with, I'm going to call that item 1. And I'm going to call this one that I ended up with after all this fiddling around item 2. Now, what I'm going to do is I'm going to take item 1, and from the left-hand side, I'm going to multiply that through by X conjugate transpose. Oops. I'm going to multiply by X conjugate transpose here. That's going to get me to a new version of number 1. And number 2, I'm going to multiply on the right-hand side by just an X. Okay, so here I'm going to end up with oops, sorry, I said I was multiplying from the left. So I'm going to end up with X conjugate transpose AX is equal to X conjugate transpose times lambda X. And my other one over here, I'm going to end up with a X conjugate transpose AX is equal to lambda conjugate X conjugate transpose X, right? And ultimately here, notice that these guys are the same. So what that means is that I can take these two pieces of information, shove them together, and find out that X conjugate transpose lambda X is equal to lambda conjugate X conjugate transpose X. And then since lambda is a scalar, I can factor that out here. So I'm going to get lambda, oh, Joe, nice handwriting. Oops, that's the wrong symbol. I'm going to get lambda times X conjugate transpose X is going to equal lambda conjugate times X conjugate transpose X. And remember that thing about the complex dot product is a little different than the regular one? This is actually just a dot product between X and X. So this thing here is the magnitude of the vector X squared. Same with this thing here. That's magnitude of x squared. And so what I can do is, since x is an eigenvector, it's not the zero vector. So it must have a positive length. I can divide through by that, and I'm going to find out that lambda is lambda conjugate. That means that my eigenvalue is actually just a real number. So that's my first claim done. Sorted. Okay, let's go collect that other claim. So, claim 2, the eigenvalues of the eigenvectors of a real symmetric matrix can be chosen to be orthonormal. Should be noted, I'm going to revise this a little bit because I don't actually have the full generality here. So there's a kind of nasty way to show that it's okay for repeated eigenvectors. So I'm going to make this little modification. My modification is I'm going to say the eigenvectors for different eigenvalues can be chosen to be orthonormal. Now, I'm going to rephrase this real quick to this claim 2 minus, which is going to be equivalent. So my claim 2 minus is going to be the eigenvector. So the eigenvectors of a real symmetric matrix for different eigenvalues are perpendicular. Okay. In other words, I'm going to show just the ortho part by itself, and the normal part we're going to get for free, because you can always scale an eigenvector and it's still going to be an eigenvector. So my plan for this is I'm just going to say, all right, what does it mean to be an eigenpair? So I'm going to write that down as I've got AX is like lambda 1x, and I've also got AY is lambda 2y. And I'm assuming that these are different eigenvalues. So lambda 1 isn't lambda 2. That's kind of my assumption here. Whoops, I switched to green. Sorry. Okay, so what I'm going to do with these guys is I'm going to write down lambda 1 times x dotted with y. And I'm going to say, all right, that's equal to lambda 1 x transpose y, which is, let's see, well, lambda 1 x is actually ax all transposed times y. And if I transpose ax, I get x transpose a transpose y. And I know what a transpose is. That's the same as a because it's symmetric. So I get x transpose times ay. But I know what ay is because y is an eigenvector. Ay is x. I get a hex transpose, and then ay is a lambda 2y. And then since lambda 2 is a scalar, I can factor that up front. And I can say this is lambda 2 times x transpose y, which is lambda 2 times x dotted with y. Now, if you've been paying fairly close attention to me over the last little bit here, you probably remember that, hey, Joe, that's not actually what you said the dot product was. You said the dot product for a possibly complex thing is actually the transpose of times the conjugate, and that's true. So I need this little claim down here that I'm just going to throw in here, and I'm just going to throw this in a little bit dirty. So note, since a and lambda are real, right? So I'm looking at a symmetric matrix. I know a real symmetric matrix has real eigenvalues. So for any eigenvalue at all, a and lambda are real. What that would mean is that AX is lambda x, right? And then I could rearrange this equation. So this is the same thing as a minus lambda I times our vector x is equal to the 0 vector. That implies that x is in the null space of a minus lambda I. And since a is real and lambda is real, a minus lambda I is a real matrix, and so its null space is made of real vectors. So that implies that x is a real vector. What I mean by x being a real vector, right, is the same thing as I mean when I say that a matrix is a real matrix. I mean that all the entries are real. So this is why I can kind of get away with rewriting the dot product as a transpose. It's a bit much to throw that in the front, but whatever. So out of this, right, I've got lambda 1 times this dot product is lambda 2 times this dot product. So that means that I ought to be able to, like, take those two equations. So lambda 1 times x dot y is lambda 2 times x dot y. Should be able to subtract this crap to the other side. Remember, here we're working with scalars, right? So I got lambda 1 times x dotted with y minus lambda 2 times x dotted with y is equal to the 0 scalar, right? And out of these, I can factor in x dotted with y. So I got lambda 1 minus lambda 2 times x dot y is equal to 0. That means that either the eigenvalues were the same, which I said they're not, or the dot product has to be 0. So that implies that x is actually perpendicular to y. Phenomenal. That's done there. Now, all I have to do to get my claim 3 is go back up to the top here and say, all right, so if A is a real symmetric matrix, then, well, I know the eigenvectors are perpendicular as long as the eigenvalues are different. So I'm going to just go ahead and assume that I have different eigenvalues. If you want to see the full generality, you do need to, like, go explore Shur's theorem a little bit. But for us, I'm going to go ahead and just say, all right, I know that the eigenvalues are real. Because the eigenvalues are real, and I have a real symmetric matrix, I know that I can pick the eigenvectors to be perpendicular to one another. Then I know, because eigenvectors are only eigenvectors up to a scalar, I can scale them all to unit length. And then that means that I can write my diagonalization, right, as Q is an orthonormal or an orthogonal matrix because all of the vectors in Q can be picked to be orthonormal. Lambda can just be my diagonal matrix with my real eigenvalues down the diagonal. And Q transpose is actually Q inverse because Q is a square matrix that's orthogonal. That's this done. This is a little bit of a head twister, I know, because there's a lot of moving pieces here. But the spectral theorem is one of the most complicated things we talk about in this course. So if your head's feeling a little bit twisted, that's okay. You maybe go back and rewatch the video. Thank you guys for watching today. I appreciate the time and effort.